Welcome to Breadboarding. This is video 6 of the Breadboard video controller series, and this is the second part of step 4, where I'm looking to replace a number of the standard logic chips with a programmable logic device, or a GAL as it's sometimes also known. So this is step number 4 in our series. Now, I was going to do this as part of number 5, but I felt that it's probably easier to replace the logic chips with the PLD before we start to add the 32K video RAM. The board's going to get a lot more messy here because of this larger size video RAM is not dual port, and so it does require multiplexing the address and data signals, which will make the layout a little bit more confusing. So we're just going to look at replacing some of the logic chips. So this is a photo of the board as we had at the end of the previous video, and you may remember that we added 2 flip-flops, one here, one here. We added an XOR gate to handle the cursor, and we've also got the inverters that we were using for the horizontal and vertical synchronization signals. There's the counter that was dividing the 25 megahertz crystal here down to provide 3.1 megahertz clock signal, which is used to feed the CRTC, and as part of that there's also a triple NAND gate which is used to provide the clear signal, so we actually clear the counter on 8 rather than the 16, which is capable of going to. So what we're going to do in this video is remove this chip, this chip, this chip, this one, and this one with a single 24-pin programmable logic device, or a GAL. So this is the block diagram that we had, and all I've done here is just highlighted the chips that we're going to be replacing with the single PLD. So this will make the board quite a bit simpler, and when we start to add the multiplexers and things for the video RAM, then it should make things a little bit simpler. And this is the schematic for the version 6 NanoComp. And we can see here again the 2 flip-flops, the XOR, the counter and its NAND, and the various inverters that we've got for the display enable and for the horizontal sync. So the programmable logic devices, we covered a number of videos back when we were replacing the address decoder with a PLD. The GAL generic array logic from Lattice and the Atmel ATF22 VL10 is what I'm using in this particular video. They're very similar, if not identical, and they have a clock pin, a number of inputs and a number of outputs, which can also be inputs. And in fact, the 22 refers to up to 22 inputs, and the 10 refers to 10 outputs. So we can have any mixture of those. And what I've got here, this is output of the WinCUPL documentation file that just shows the pinouts that I've defined for this, and we'll cover what these pinouts are in a minute or two. If we look at the data sheets for the Atmel chip that we're using, this is the 22LV10 which we're using. Unfortunately, this particular data sheet, the section here that shows the main fuses which are able to determine the function of the chip is not very clear. So if we look at a similar Atmel chip, you can see here this one's a lot clearer, and what you can see here is the dual inline DIPS pinouts are the first one, the surface mount is the second one. So pin 1 is a common clock, so there's only one clock that can be used for all of these output logic cells. Now the output logic cells include a D flip-flop or D latch, and so we can only use one clock to toggle those, and that will be an issue when we come to look at the counter in a minute. And each of the inputs can be patched into the inputs of all these other cells. You'll see that there are some cells in the middle that can have up to 16 inputs, whereas some of the others at the end can only do 8. So if you're doing more complex designs, you might find only certain pins would have the right number of connections to be able to do the design. So the pins that you choose may be constrained by the number of connections that you've got coming into them. In our particular case, we're not coming anywhere near that, so it's not an issue. So the key thing is here, the input can either be normal or inverted, and we've got the ANDing mechanism is through this matrix here, so we can do any AND or NAND effectively here, and there's an OR here, and because we can also do the invert of those, then we can also do NORs as well. Now, the documentation on the Atmel PLDs isn't quite as good as for the GAL. So although they're identical really, but the GAL does show these macro cells more clearly. So for each of these you've got an OR where all of the various lines coming in from the AND matrix come in here, and then we've got a D latch or D flip-flop. The clock is a common clock signal, the D is the input, and then there's an asynchronous reset and a synchronous preset. And again, those are shared between all the latches. Asynchronous reset basically just clears everything as soon as the signal is activated, whereas a synchronous preset will set all of the outputs to 1 on the next rising clock. This 4-to-1 multiplexer is able to determine how the logic here works. And there are 2 fuses known as S0 and S1 that determine which of these 4-way configurations are in use. And they're actually explained a little bit better below here. So in the registered mode, we have the flip-flop. The output of the OR gate goes into the flip-flop D and then comes out of here, and we can either have it active low or active high. So you can see here with S0 and S1 is 0, 0, or if S0 is 1, then it means that we have the active high rather than active low. And then in the combinational mode, then we're ignoring the latch or flip-flop, and in this particular case we're taking the active low, and in this case we've got active high. So this multiplexer that we've got here is determined by those S0 and S1 signals. Now when you look at the WinCUPL software, which is used to compile the definitions for these PLDs into a file that we can then use to burn using the EPROM programmer, there is a document dev help that lists the capabilities of each of the chips. And for our ATF22V10 chips, there is a section here that tells us that it's 24 pins, the number of product terms, which are the number of combinations of the fuses and things we can have. But it also tells us these extensions. And what this means is that we can have output enable, a D latch input, asynchronous reset, and synchronous presets are additional terms that we can have when we're defining the pin definitions, and we'll see what that means when we get into the definition for the PLD file. Now, trying to find this information, it wasn't particularly clear, and it's not particularly easy to find this information. Once you see an example though, it's fairly obvious, but trying to find the right example was a little bit challenging. Now when we look at the counter that we're trying to replace, this is the 74LS163 or ALS163, and you can see here this is the logic diagram of the chip. Now we don't really need to worry about all of this sort of load, enable signals and clocks and things like that. The clock signal obviously will be used in this particular scenario, but the key thing is here these are D latches or D flip-flops, and you can see that the negative output is actually feeding back in through to the D input here, and that's one of the key features of these types of counters that we need to implement. Now if we go back to our slide, trying to define that was quite challenging, but I did find a link here which I include in the URL in the description below, and after a lot of searching I did find an example with a similar GAL. So it's a 16V8, so this means 16 inputs and 8 outputs, but this actually includes quite a neat explanation of how to do this and why you need to do it like this. He's using Q1, Q2, Q3 rather than QA, B, C, but it's the same idea. So the key thing is down here is he's defined pin 1 as clock, which is standard for these chips. He's defined a pin 2 as clear. Now we don't need a clear signal in this particular case, so we're not going to implement that. And then we've got a Q0, Q1, Q2, and we're just going to replace that with QA, B, C. And you can see here that for Q0 or QA is in our case, that the D input is just the inverse of the QA or Q0 output. There is the clear term in here as well, but again we don't need to worry about the clear. Then for the next one, then you can see that there's the logic here which basically determines the conditions with the Q1, Q0, QB, QA that we need for toggling, and then finally for the Q2 signal as well. We can ignore Q3 or QD in this particular case. So this is what we need to do to enable a counter in our PLD. And so what I'm going to do now is to show you the PLD configuration file. So I have the pin out here, and I'll explain what these signals are as we go through. So I have the inputs. So we have our 25 megahertz dot clock, the shift register dot output. So this is the serialized stream of bits from the rasterized character that determines we're a 1 or for a foreground character, 0 for background character. The cursor signal from the CRTC, the display enable input from the CRTC, some not connected pins just because we need more of the outputs than we need of inputs. The invert horizontal sync and invert vertical sync, if these are held high, then the horizontal and vertical sync signals will get inverted, so we'll get a negative synchronization or positive synchronization. We've got the horizontal sync in and vertical sync in. Then on the outputs, we've got the foreground background output bit stream. So this is the output which has been XORed between the cursor signal and the shift register dot out, and this is able to then go into the multiplexer to determine whether you have the foreground or background colours. The display enable out, which is in fact display enable out, is inverted and delayed by 2 dot clock cycles. The DE1's an intermediate signal. The clear signal is the NAND of the QA, QB, QC values, which was the original latch signal that we were using until we worked out we needed to delay it. We then have the QA, QB, QC, so that's the counter divide by 2, divide by 4, divide by 8 signals. Then our shift register latch signal, which is the clear signal effectively delayed by 4 clock cycles. Now in fact, we're not delaying the signal by 4 clock cycles using flip-flops. What we're actually doing is, having done this analysis of the values of QA, QB, QC and how to get the right signals here, we can actually achieve the same result just by using some logic to produce the same signal. So in this particular case, the original QA, QBC signals, when all of them were 1, then the output of the NAND, triple input NAND, would be 0, and all other circumstances it was 1. But then we wanted to do is then delay this by 4 clock cycles, so this would actually take it to here. Now in fact, I looked at these values, and if we NAND QA and QB together, we get a 0 here, and we also get a 0 here. Now we don't want it in this position, but if we then OR the output of here with the C value, then here we get a 0 and here we get a 1. So if we NAND QA, QB and then OR that result with QC, we get the same signals if we delayed the original clear signal by 4 clock cycles. So it's a bit simpler to implement in the PLD and doesn't require 4 gates or 4 output pins to do this. So then we've got the horizontal sync out and vertical sync out, which again will be inverted if the other pins are true. So within the equations here, then an exclamation mark is a not. The hash symbol or number symbol for Americans is an OR. The ampersand and is and the dollar sign is actually an exclusive OR, an XOR. Now there aren't any XOR gates actually on the PLD, but the compiler converts XORs into the appropriate combination of logic gates. And then the .D means use the D input to the flip-flop latch for that particular line. So what we're defining here is the clock is the dot clock input pin. The foreground background output is just the cursor exclusive ORed with the shift register dot output. We're then mapping the display enable input to the first D flip-flop latch, and then the inverted output of that is then going into the D out. So our output should be delayed by 2 clock cycles and also inverted. Then we've got our equations, as I just covered in that link in the web browser. So we've got our QAD is fed the inverted QA output, and then the B and the C inputs then defined by these equations that we covered in that link. Then we've got the clear, which at the moment I'm just ANDing QA, QB, QC, and then because we are defining the clear signal as the not of clear, so if this works out the same. So it's effectively the NAND of the QA, QB, QC signals. The shift register latch is now defined as that equation which we talked about in the spreadsheet. So that is the NAND of QA, QB, then ORed with QC. And then these two signals here, the horizontal sync out, if the invert signal is 0, then we just get the standard horizontal sync as it is. If the invert horizontal sync is true, then we get the inverted value of the horizontal sync out, and the same for vertical sync. So in order to compile these, so now we're going to open the PLD file in WinCPL. This is the Atmel utility used for compiling the PLD file into the .jed file needed to program the PLD in an EPROM programmer. So if we just run the device-dependent compile, and you'll see that's successful. And if we look at the warnings here, anything it's telling us here is that some of our cells which are using the D registers, it's just telling us that we don't have the AR and SP values set for those, which is not a problem. So that's not an issue. And then if we were to have a look at the output files from that, so if we just look at the output file from that, so we've got our VGA JED file, and this is the output file that's needed to program the PLD. I'm also going to show you, I have produced a chip label for this. So you can see over on the left hand side here, this is a generic one that I used when I was doing the address decoder. So we have the inputs going from I1 all the way to 11, and then the input outputs from 0 down to 9. And all I've done here is I've abbreviated some of these symbols. So we've got the horizontal sync, vertical sync, shift register out, and various other things. So when we stick these on the chips, it just makes it a bit easier to hook up. And I've also updated the KiCad diagram. So I've now removed the logic chips. You can see here now that the 6 logic chips have been removed, and now we just have this PLD which is hooked into all the signals and all the output signals. There are a few of the signals are coming all the way down here, but that should give us a lot more space for replacing this chip here in the future video with the multiplexers and the buffers and things which are needed to handle the single port RAM as opposed to dual port RAM. So you can see here I've installed the PLD over onto the left hand side here, and what I've done is I've hooked up the logic analyzer to a lot of the current signals which are still being fed off the existing logic chips, and then I've also used the same colour signal on the second row of pins. So you've got sort of 1 to 8 and 9 to 16, and what I've done is use the same colours for the same signals. And what we're going to do is to start this up, run it so that we can see the display on the monitor, and then what we're going to do is to use the KingstFizz logic analyzer to look at what the values and things are, so we can see whether or not the timing appears to be the same. So I've powered up the Nanocomp, and we're just going to load the test program. So I'm just going to hit load, send file, and we just execute 000. So now we just need to send the character. So we just need to send the VGA 16 characters. So I'll now load this again. Send file. And as we load that, you can see the display actually populate as that's going. So that's all working okay. Okay, so the video card is now working. Now we're going to look at KingstFizz. This is the logic analyzer software, and what I've done is hooked up pin 0 to 7 are plugged into the original logic values on the current working board, and then pin 8 to 15 is now plugged into the PLD equivalent signals. So this is triggered on the rising edge of video sync, so this will be at the beginning of the page. So if we run this, it's running at 200 megahertz, so this can resolve down to about 5 nanoseconds in time. So what we can see at the top is the video sync signals and the corresponding PLD version. And if we look here, the cycle here is a frequency of about 59 hertz, or about period of 16.9 milliseconds. So that looks about the same for both of these. And if we zoom now down into the first page, now we can see also that during the vertical sync period, then the display enable is blocked out. So we can see that display enable will not show anything around the vertical blanking area, and then as we come to each horizontal line, then there's a period at the beginning and end of each line where we're not displaying anything either. And then we can see when the display enable goes low after the beginning of the page that we start to show data. So this is the foreground, background dot clock. Now the key thing is here is that because display enable is high here, then whatever is here will not be shown, and that when we were tuning our display enable signal, then these would have been the stray characters that were appearing. And if we take some markers, so if we take some marker pins, so if we put A1 at the beginning here, and we make A2 the beginning of the display enable, if we were to count how many of these there are, we can actually do pulse counters as well actually. So can we... Let's not, won't bother with that for the moment. What we can do here is you can see how many horizontal lines are there between the vertical sync and our data starting to be displayed on the screen. If we have a look here, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. But if we go and have a look at our source code for this, we can see that the vertical total adjust is 14, which is 20 decimal. So in fact, what this shows is we've got 20 lines at the beginning of the page, which is the vertical adjust. And then after that, we start to display values. Probably the first 2 rows are going to be just blue, which from looking at the display, it looks like the first 2 rows will be blank. And then after that, we start to see the bit data. And if we look at the bit data, we can see that in fact it looks pretty similar. So we've got almost identical information coming out there. If we have a look at the other clocks, in this particular case, the clock signals are pretty much matching, so that's good. There's a slight delay here. I suspect the chips we're using for the PLDs are slightly faster, perhaps, than the clocks. There seem to be. So that width there is 45 nanoseconds and 35 nanoseconds. This is 40 nanoseconds and 40 nanoseconds. So this can just be down to the sampling rate we've got here. 200 megahertz is able to resolve down to 5 nanoseconds. So if you were just slightly delayed from that, then it would sort of fall in the middle of 2 5 nanosecond slices. And if we look at the other signals, then we can see here that our original character clock here, which is driving the current CRTC, and the one from the PLD are actually a little bit out of phase. Now, I was thinking about this, and I think this is due to the fact that the reset of the counter will occur at different points. So the PLD will reset at a different point in time from the old 163 counter. But because the CRTC is running off this clock and not this clock, then you'll see a difference. But I think as long as the relative gap between these things is correct, so if we take a look here at the gap between the clear signal here, you can see the clear signal here and here is in the last part of this, is in the last one clock cycle of this area here. And if we look at the same ones for the PLD ones, then these are also falling in the same period. So I think these are just offset by half a clock cycle here, and it's just dependent on when the reset occurs of the counter, where it starts counting from. So I don't think it causes a problem, because when we run the CRTC off this signal here, then it should all be in step. So it looks like the signals are all coming out pretty good. So they're all certainly the right order of magnitude. They're lined up, with the exception of these clock signals, and I think we can understand that because the way how the counters are starting and resetting will be slightly different depending on how the chips themselves power up. So it looks pretty good. So I think what we're going to be able to do now is to go back to the board and to start replacing the current chips. So what we're going to be doing is to pull out the chips up here and start wiring this in, and I'll refer to the schematic diagram as we go through and do that. What I will do though is I'll record this and speed it up, and then I'll perhaps comment over it afterwards, but hopefully this next bit shouldn't take very long, and then we'll come back and see if we can get the board working with the simplified PLD design. So first of all, we're going to remove all of the logic analyzer. Then we're going to remove a lot of the fly leads that we had from the earlier video. Start to remove the chips and unwire some of the fixed wiring that we already have there. Those are the 6 chips. This is our PLD. Let's check the diagram. So I wired this in, but then I decided to adjust it so that the vertical sync would be level with that yellow lead coming in there. It means we didn't have to rewire that bit. So wiring in the horizontal sync, vertical sync, and the invert signals are wired high, so that means we get the inverted video signals for sync and horizontal sync coming out of there. That's wired in. Now we're going to check various other signals. So the shift register latch signal, just hook that in. Then we're looking at the dot clock there. Just make sure the dot clock is distributed to where it needs to go and hooked into the PLD clock there. Now we're going to hook in the display enable to the buffer enable. And then we're also now going to wire in the foreground background output into the multiplexer that chooses which of the foreground and background colours are being used. So now we're plugging in the shift register output from QH all the way up to the SRO pin, now the cursor output from the CRTC, and the display enable from the CRTC now going into the PLD. Just remove some of the old links and things, so tidying things up. Just put in the character clock onto QC. Just check everything over, and that should be it. I think I've wired in everything. So we have the character clock there to QC. We have display enable, cursor. We have horizontal sync and vertical sync. So yellow is vertical sync. White is horizontal sync. Those are going off there. Then we have the shift register latch that is at SL. We have the output going to shift register out. We have the clock going down here. Clock, dot clock goes round to this pin here, and then the display enable is going out to our multiplexer there. Sorry, not the multiplexer, it's going out to the buffer there, so it turns off the output when display enable is preventing it. And then this is our multiplexer, and we have the foreground background select that goes to foreground background there. So I think we have it all wired in. So now what we're going to do is to switch it on, see if it runs up. So the monitor has loaded, that's good. So now we're just going to load up the software for it. I will need to put this into ROM sometime, so I'm just going to load the VGA fonts first, which takes a little while. Once that has finished, then we'll load the CRT2 rec, and we'll send that. That's finished, and if we now go 000, and we'll check our display. So the display appears to be working absolutely fine, and what I will do is I will plug this into the video capture card. So let's just go to the VGA capture card, and you can see here that our output looks pretty good, almost unnoticeable from the original. So that looks like it's working okay. So what we've been able to do here is, so we swapped out these circuits. We've redesigned things slightly in that we're now relying on the PLD to provide some of the timing where we were using these flip-flops, and these items here have now been replaced by the PLD. Now in the next video what we're going to be doing is, it's going to get a bit messy in that the dual port video RAM that we've got here at the moment, which is the larger 48-pin chips, has the benefit of having obviously data and address pins on both sides. However, we're going to be installing some higher capacity 32K RAMs, which are very fast. The only problem with them is they only have one set of data lines and one set of address lines. So we're going to have to hook up some data buffers and some address multiplexing so that both the CRTC and the CPU are able to access the data. And we're also going to have to worry about when the CPU is accessing the RAM, what happens to the CRTC. So that'll be in the next video. So if you don't want to miss out on future videos, please hit subscribe, and if you found it interesting, please hit like. So in the next video I'll be swapping out the dual port video RAM for some larger RAM, and that's going to allow us to be able to do color characters by individual cells, and then in later videos after that we're going to start enabling a graphic output so we can do fairly high resolution graphics. Thanks for watching.